Well, hello. Today we'll be talking about chords. Well, if you're familiar with music, you're already familiar with chords, and this has nothing to do with those chords, even though they're spelled the same. A musical chord is 3 or more notes played all at once. That group of notes was originally called an accord. A chord can be used as a noun. If you've seen Pirates of the Caribbean, you already know that. I'm sure there are several places, I think, in that movie where someone says, "We have an accord." Well, that referred to the notes, which seemed to be in agreement or were harmonious with each other. So when they played a group of notes all at once, it was called an accord, which, musicians, they like slang, so they just shortened it to chord. Well, after that, confusion with the mathematical chord led to a common spelling of C-H-O-R-D for the musical chord. So if you're wondering what the relationship is between musical chords and the chords on a circle, even though music is very mathematical, in this case the connection is completely accidental. Or you could say it's just the result of mistakes made by people who didn't own dictionaries, I guess. Well, and by the way, music is extremely mathematical. This just happens to be a case where the connection is accidental. Frequently, the connection between mathematics and music is not accidental at all. Very direct connection. But this is not a music course, so let's get on with it. A diameter is a chord. Anything that connects 2 points on the circumference of a circle, that's a chord. Diameter, of course, is a special chord which runs through the center of the circle. Otherwise, it's just called a chord. Diameter is rarely referred to as a chord, but it has the properties of a chord. So if you need to use one of the properties of a chord to demonstrate the truth of some proposition, you can then treat the diameter as a chord if it helps. But don't treat a chord like a diameter. The properties of diameters do not apply to all chords, but the properties of chords do apply to diameters. And I think it's pretty obvious that this particular chord cuts the circle in half, or 2 congruent arcs. Here's one arc, measure 180 degrees, and here's another arc with a measure 180 degrees, and they are in fact congruent because they're on the same circle. Arcs with equal measure on the same circle or on a congruent circle would themselves be congruent. This regular old run-of-the-mill type chord, this again breaks the circle up into 2 arcs, a minor arc, AB, and a major arc, which I would have to put a point over here if I wanted to describe the major arc, because remember, we always call the small one just by the 2 endpoints. The large one, we have to include some middle point to make it clear that we're talking about the major arc. So the chord breaks us up into ADB and AB. Naturally, since we've got a bunch of terms at this point, we've got circles, diameters, chords, secants, all kinds of stuff. It's about time we had some theorems about all this stuff too, isn't it? Well, you're in luck if you were waiting for that. They're here. We've got several theorems involving these chord thingies. And the first one is that if the minor arcs are congruent, then the chords connecting their endpoints are congruent. How would we know that? Well, this is a pretty easy one. Now let's take a look at this by drawing another circle that's a little easier to work with, I think. Well, it's easier for me to work with anyway. They say that AB is congruent to CB if the arc AB is congruent to the arc CD, and vice versa. Well, let's start with the arcs being congruent. What does that mean? If AB is congruent to CD, that means they have the same measure. And how do we measure an arc? Well, by the angle that it subtends. That means this is, say, alpha. Then this is also alpha. These two angles have to be equal. Well, what about these sides of this triangle I created with the chord here? Well, these are all radii, aren't they? Yes. This is the center of the circle. I'm not very good at picking centers, so it might be a bit off. But it's fairly obvious now that these two triangles I created by just connecting the radii to the chords are congruent. Side, angle, side. These two sides are congruent because radii are all equal. And these two angles are congruent because they are the angle of congruent arcs, or the measure of congruent arcs. So, side, angle, side says that these two triangles are congruent, thus AB, from corresponding parts of congruent triangles being congruent, AB must be congruent to CD. That's pretty simple. And if we go the other way, well, again, R and R are congruent, and if we know that the segment AB is congruent to CD, well, now we've got side, side, side congruence. We don't know what the angles here are from a triangle. Remember, arcs and opposite sides aren't quite the same thing. We measure an arc by the angle that created it. We don't measure sides that way. However, since this side is congruent to this side, that is, AB is congruent to CD, and naturally these two sides, all the other sides are congruent because they're all radii. So by side, 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 we know that these two triangles are congruent. That means that this angle must equal this angle. In other words, for the second part, I didn't originally know that these two angles were equal, but side, side, side tells us that two triangles are congruent, and once again, corresponding parts of congruent triangles are congruent, tells us that these two angles are congruent, which leads to the fact that the arcs are congruent since they subtend the same angle on the same circle. Boom. That's the whole thing. Not much to it. And actually, I think you'd probably figure it was kind of obvious, wouldn't you? I mean, think about how this could not be true. I'd have a hard time envisioning a situation where two identical arcs, two congruent arcs on the same circle, would have different chords of different lengths. And it's hard to picture that happening, and that's good because it can't happen. And here's a couple more pretty simple theorems that we'll use in the problems. If we've got basically two chords, really, which are perpendicular and one bisects the other, well, then the bisector is a diameter. Which kind of makes sense. I mean, think about it. If you were cutting the middle of this arc, going straight to the other side, perpendicular to the chord that created the arc, try to think of a way you could do this that wouldn't take you through the center of the circle. Say this is the center right here. See if there's a way you could do that, where this line would be over here somewhere or over here and not go through the center of the circle. Fool around with that and you'll easily see the truth of this theorem, because you won't be able to find a way to get this line somewhere else. And it pretty much works down here too. They're fairly easy to understand and see sense of these two things. This is just the converse of this one, so we could have made it one theorem into an if and only if statement. Here we have that if the diameter is perpendicular to a chord, then the diameter bisects that chord. And again, it makes good sense. One thing you could do is, say, draw a segment from the center to the point of intersection here, and the center to the point of intersection here, and then the bisector, and you've got two congruent right triangles, and it'd be pretty easy to show that this bisector has to actually go through the center of the circle. And you can do something similar down here. I'm going to let you guys play around with it and convince yourself that this is actually true. Now here's another way to look at it. It's not really a proof, but I'd be able to see the sense of the whole thing. Let's take a chord. Well, what is a chord? It's just a line segment, right? Now, this is the kind of thing that's really hard to prove. Probably should be an axiom. Given any segment, I think I could say, and you could too, that any segment could be the side of a triangle. And it could probably be the side of just about any triangle, as long as that triangle had one side equal to the length of this segment. That sounds not so obvious it's hardly worth stating, but the fact is, I've never actually seen the theorem or axiom which says that a line segment could be part of a triangle. Always. There is no such thing as a line segment which could not be part of a triangle. So let's consider this chord as part of a triangle. Well, what does that do for us? Suppose we were to draw, just finish this off, create some triangle. Doesn't even matter what triangle we draw. Just draw some triangle with this as one side. There's going to be a third vertex. After all, this will be a point at a vertex here when we connect up some segment to this segment. It could go off that way, it could come down this way, it could do a lot of things. But the third vertex will be somewhere on the circle. Suppose I put it here. What the heck? As good a point as any, right? Well, if I go ahead and connect these points here, I've got a triangle. Okay, so what? Remember that theorem way back a while ago which said that the perpendicular bisectors intersect at a point which would be the center of a circumscribed circle? In other words, a circle which passed through each vertex of the triangle. You could also say it's the point which is equidistant from each vertex, and we arrive at that point by producing perpendicular bisectors to each side of the triangle. Actually, we only need two sides, and the point where they intersect, that will be the center. If I draw a perpendicular bisector from any side of this triangle, it will have to pass through the center of the circle on which I have inscribed this triangle. Well, this was the original one we were worried about. Now, if we look at this, after we've drawn in these triangles, it's very easy to see that the perpendicular bisector of this segment has to pass through the center of the circle, which we can circumscribe on the triangle once we've created a third point out here. So the relationship between perpendicular bisectors and the center of the circumscribed circle actually comes straight from previous chapters. And that's another way that you could at least convince yourself of the truth of this, that this right here, well, if we continue up, oops, naturally we have, that goes through the center. If we just continue this line to the circumference, we have a diameter. So the properties of perpendicular bisectors of a triangle can also be used to convince yourself that the perpendicular bisector of a segment has to pass through the center of the circle. Just think of the segment as one side of a triangle that you can't see the rest of. You can't see these two parts, but they're there. That's just a way to look at it. If it helps you remember it, cool. Now here we have a problem where they ask us to find x, and this circle is called circle Q. So we know Q is the center. So now we have an obvious case of our previous theorem. A diameter which is perpendicular to the chord bisects that chord. Remember, we had one theorem which said if we have a perpendicular bisector of a chord, that perpendicular bisector must be a diameter. Here we have a diameter which is perpendicular to the chord and therefore bisects it. So all we have to do is set these two. We're supposed to find x. To do that, all we have to do is set these two segments equal and get that 5x minus 6 equals 2x plus 9. Well, if we do that, we do a little rearranging, add 6 to each side, subtract 2x from each, get that 3x equals 15, x equals 5. Does that work? Well, let's try it. This is 25 minus 6, and it should be 19, right? Okay. This is 10 plus 9. Well, that's 19 also. Not a very good 9, but... So it works. Well, here we have one. Doesn't look too bad. This diagram isn't too awful. I know, chapter 9 of this chapter, some of these diagrams, I don't know, they can make me dizzy after a while. I get confused as to what the heck it is I'm looking at. But we're stuck with it, so this one isn't too bad. And the question is, anyway, which congruence relation is not necessarily true? Well, if we can steady the ship and avoid getting seasick while we look at this diagram here, I would say, see, PQ and QN. Well, we have a diameter here, perpendicular to the chord, so it bisects it. So we do know that these two are congruent. So this is true. What about this? NL and LP. Here's NL, and here's LP. Well, this is pretty easy to see that this has to be true. Why? Well, we have a right angle here, right? It's just these two lines are perpendicular, which means we have a right triangle from LQP and another right triangle, LQN. Well, this leg, pardon me, yeah, we can call it a leg. This leg of the triangle is congruent to this leg. This leg is congruent to itself. And of course, they're both a right angle. So we have special theorems for right triangles, but the ordinary theorems work for them too. And if you don't remember the special theorem, you can always use the regular theorem. The regular theorem is side, angle, side. These are both right angles. In fact, most of the special, in fact, I think all of the theorems which are specific to right triangles and work for right triangles work because you know ahead of time that you have congruent angles at least one point. That makes a big difference. You're starting with two congruent angles, namely the two right angles. So LP and LN being the hypotenuses or hypotenuse. I still haven't found out which is right. They have to be congruent because of, well, partly because of corresponding parts of congruent triangles being congruent, and partly because if PQ is the same as QN, and of course LQ is the same as itself, if we take this squared plus this squared to get this length, and then take this squared plus this squared, we're going to get exactly the same thing because they're all equal. So there's a couple of ways that you could show very easily that LP and LN are definitely congruent. What about MN and MP? These are the arcs. Well, these are arcs on the same circle, subtended by the same angle. So we know they're congruent very easily. Well, what about PN and PL? We've got this chord here, and then this chord. Well, this looks like an equilateral triangle, but it's not immediately obvious that this, which is the hypotenuse of this right triangle, is equal to, say, 2 times this leg. After all, PN right here is the entire chord, which is broken up into PQ and QN, which we treated as legs of 2 different congruent right triangles. So you could say that the length of this is 2 times PQ. Well, if PL was congruent to this, then PL would be 2 times PQ. But PL is the hypotenuse of this. When it turns out to be exactly double PQ, that's kind of shaky, and there's no way to see that that's going to automatically be true from this diagram. Just for fun, I laid out a quick equation to see if it was even possible for that to happen. If this hypotenuse could be double this leg, and it definitely is possible, what you have to do is think of this segment here, PQ, as having length L. Well, if the hypotenuse is equal to PN, that means it's equal to 2L. This is L. The whole thing would be twice that. So for the hypotenuse to be 2L, that means that 2L squared equals the sum of the legs squared, which is L squared plus H squared. I'm calling LQ H. Kind of looks like a height. Anyway, for any reason or no reason, I called it H. So we square everything at 4L squared equals L squared plus H squared. So if H squared equals 3L squared, we could in fact have a right triangle with the hypotenuse equal to double one of the legs. The question is that the case here? And there's no way to know that it is. So D is the one which is not necessarily true. And they were smart to write necessarily because it actually could be true if you had some way of showing that this segment right here was 3 times the length of this segment. You would have a hypotenuse that is actually double this. But we don't have any way to know that. So the correct choice is D. Well, looks like somebody tried to diagram a circle and possibly made a mistake. Let's see here. Aha. These are both chords. They're cut perpendicularly by a line pass or a segment passing through the center, which makes it a diameter. Cut perpendicularly by a diameter means that it's a bisector. So we know that at least this part's right. This in the sense that each CG and GD should be equal and have equal measure, be congruent. And EH and HF should also be congruent. However, we might have a small problem with the actual numbers here. This problem, intuitively, you can probably guess that these 2 chords have to be the same length because they're the same distance from the center along a diameter. Intuitively, that looks sensible. But can we make it official? Yeah. There's a theorem. It says pretty much exactly that. In the same circle or congruent circles, two chords are congruent if and only if they're equidistant from the center. Well, remember, the distance from a point to the line is defined as the perpendicular distance. You have to be able to draw a line perpendicular to the original line, which goes out to that point, and that is defined as the distance from the point to the line. And if you're wondering, why the heck would this even be true? Well, suppose, maybe I should redraw this larger so you can see what's going on here. Now I just took the original over here and exploded it. Boom. Now if I draw in some extra lines here, create some right triangles, I probably can demonstrate some congruence, which will show that this has to be true. How are we going to do that? Well, number one, by definition, they are equidistant, which means this perpendicular line to the center and this perpendicular line to the center, they're both equal. We don't know what they are, but they're congruent. So FE and GE, they're congruent. Also, if we were to extend, this is perpendicular and it connects the center. So if we were to extend this out to here, and in other words, extend this line out this way and out this way, so we have a segment that connects the two. A segment with two endpoints on the circumference of the circle, which passes through the center, is what I'm trying to say, which means we have a diameter. We have a diameter perpendicular to the chord, so we know the chord is bisected by this short segment here, because we can extend this segment into a diameter if we wanted to. So it still bisects, so this is congruent to this, and same thing's true here. So we don't know that this and this are congruent yet, so I'll have to use two different marks. But we do know that this half is congruent to this half. So what? Well, that tells us that this triangle is congruent to this triangle, but that doesn't help too much. What else does it tell us? What about this triangle and this triangle? Well, what we have here is a radius. The hypotenuse is the radius for this right triangle. The hypotenuse is the radius for this right triangle, and of course these two radii are congruent, and this side is congruent to this side. So we have an hypotenuse and a leg which are congruent, and from our right triangle theorems, this only applies to right triangles now, we have the HL theorem, which says that if the hypotenuse and one leg are congruent to the other triangle, that's good enough. Which means this triangle is congruent to this triangle, and using corresponding parts of congruent triangles being congruent, that means this side is congruent to this side, or this leg is congruent to this leg. We can use exactly the same reasoning to show that this right triangle is congruent to this right triangle, and this section is congruent to this. Well, we already know the segments just add up, so this is AF is congruent to CG, FB is congruent to GD, so AF plus FB is the same as CG plus GD, and that's probably fairly obvious intuitively. How does that apply over here? Well, now we can see that this can't be right, because these two are equidistant, but this would be a total length of 12, and this would be 14, and that's no good. To put it another way, 12 doesn't equal 14, so this must be wrong. The important part of this problem was to remember or recognize this theorem. What's wrong with this diagram? We have a chord here cut by what appears to be a diameter, and they say that the arc here, BC, is congruent to DC. Why wouldn't that be true? Well, remember, it has to be cut the perpendicular bisector. In other words, if we know for sure that this is a diameter, then it will cut this chord as a perpendicular bisector, and it will make each of these arcs congruent. Or, if we don't know it's a diameter, but we do know that this is perpendicular, then it follows that AC is a diameter and is a perpendicular bisector of DB. The big problem with this one is we don't know that AC is perpendicular to DB. If we had this in there, one of these, well then this would be true. But we don't have that, so maybe I should have done it this way. Oops. Come back. Thank you. Without the perpendicular sign in there, we don't know that this is true. It could be. After all, it kind of looks like this thing. See, we also don't know that DE. That's one of the problems with the diagram. The diagram is written in that these two are congruent, but we don't really know that they are. That's really the error in the diagram, which leads to this error. If we don't know that these two chords are congruent, then we don't know that the arcs which they produce are congruent. And vice versa, really. Now they're asking us to determine if AB is the diameter of a circle. Well, what do we have here? We have a chord which is cut by this segment. It's perpendicular to this segment, and it bisects CD, because we got 6 here and 6 here. So we have a perpendicular line or segment which bisects a chord. Means it has to be a diameter. And we're done. That's really easy. As long as it's this perpendicular bisector of a chord, then it has to be a diameter. These numbers here, this 4 and 9, that was just there to add to the confusion. They serve no purpose. They're superfluous, unnecessary, extraneous even. Now here's one that looks a little weird because they're asking us about these tiny little upper triangles here. We don't have too much information to go on, do we? They don't even tell us that P is the center of the circle. If they had written that QCR was the semicircle taken from circle P, then we would know that P was the center of the circle. But I don't think you can work this problem unless you know that P is actually the center. And it's not obvious to me how we could prove that. So I'm just going to have to assume that they meant to tell you that P was the center but forgot somehow, or maybe it was a misprint. The publisher may have left it out. So what do? Well, since PC, assuming P is the center, is a radius, and AB is congruent to PC, that means AB will be congruent to any radii, because all radii are congruent to each other. They're all the same length. So if we were to connect AP and BP, we would have an equilateral triangle. Two sides are the radii, and then the third side is congruent to any radii. So I go ahead and draw these in. Now I have an equilateral triangle. Well, so what? We're trying to prove that these two triangles up here are congruent. and I'm wasting time drawing equilateral triangles. Well, we have one more fact here, that AC, that's the arc AC, is 30 degrees. Well, we measure an arc according to the angle that it subtends. That means that APC is 30 degrees. Well, with an equilateral triangle, every angle is 60 degrees. That means that this over here is 30 degrees, and we have an angle bisector. These two sides are congruent. Well, we already know we have an equilateral triangle, and everything you can say about an isosceles triangle, you can certainly say about an equilateral triangle. And one of the things you can say about an isosceles triangle is if you draw the angle bisector between the two congruent sides, that will also be a perpendicular bisector of the opposite side. We might actually also be able to use our theorem, which says that a diameter which bisects would be perpendicular, and a diameter which is perpendicular would bisect the chord. But that doesn't seem quite so useful because, as I say, the angle bisector in an isosceles triangle automatically becomes a not just bisector, but perpendicular bisector. So, if we wanted to be circular about it, we could say that we know this is the center because this is the perpendicular bisector, and therefore PC must be part of a diameter. But that's circular because we only arrived at this perpendicular bisector conclusion by assuming that P was the center and then drawing two radii. And frankly, every way I could come up with to show that P was the center was something like that, where I had to assume P was the center in order to prove that P was the center. And that's not kosher. So we have a perpendicular bisector here. That means AD and BD are congruent. These two lines are perpendicular. That means we have a right angle here and a right angle here. Also, the chord which connects two endpoints of congruent arcs, then those chords are also congruent. In other words, we have a congruent arc here, and this arc AC is congruent to CB. That means that the chord which connects the endpoints of AC is congruent to the chord which connects the endpoints of CB. Well, those chords I just talked about are actually the hypotenuses, or hypotenusae, of these two right triangles. So what we have here is HL. That is the hypotenuse leg theorem for right triangles to show that they're congruent. This is very similar to the SSA for regular triangles, which, as we know, doesn't work. That's no good. SAS works. That's okay. But side-side angle, you can remember that if we have, let's say this angle is congruent here, this side is congruent, well, we could draw it down here, or we could draw it out here. These two sides would have the same length, so we got side-side angle, which does imply 50-50 congruence, but we're not going to work with probability theorems here. Our theorems either prove that something is always true or always false. A theorem which proves that something has a 50% probability of being true is outside of this class. So we're not going to mess with SSA, and we've already thrown that out before in other sections. But for a right triangle, that will work, and you can play around with it. Draw yourself a right triangle with a leg and hypotenuse the same, and see if there's any way you can complete that without producing a congruent right triangle. I don't think you will. And if you do, let me know. I will put you in for a Nobel Prize. So you can see that really the important parts of this problem were recognizing that if you get an equilateral triangle out of this, then 30 degrees would imply that you had an angle bisector. Once you've got the angle bisector, you're pretty much done, because then you show that these two segments are congruent. Now you know that these two arcs are congruent, because again you've bisected the angle, and the arc is measured according to the angle it subtends. Then our theorem tells us that the chords corresponding to those arcs must also be congruent, and then we have HL. And that's about it.